now. Okay. Hello. Welcome, everyone. It's my pleasure to introduce you, one of us, Jonathan. He is going to speak about universes and higher algebra in infinite category theory. So, welcome.
Thanks, Jose. Yeah, glad to see so many of you here. I'm going to talk about some joint work with Dan Gratzer and Ori Puchholz, and also a formalization project that is connected to this with joint with Nikolai Kudasov and Emily Reel, and a bunch of other contributors to that library. So I'd like to start off by dedicating this talk to Thomas Streicher, who unfortunately passed away at the very beginning of this year. So he was my PhD advisor back in Darmstadt and has had a huge influence on this work, which is also follow-up work to my PhD thesis, which he advised and contributed a lot of ideas. So some of you also knew him, especially Alexander. So I know that you shared some time in Munich together. Okay, so what is the point of this talk? So because it's Halloween, it's very scary outside. I like to kind of not contribute to the scare, but actually take some of the scare away that we have before infinity category theory. So I want to kind of explain an approach to doing infinity category theory in a non-scary way, relatively non-scary, relative to having absorbed some of the foundations of homotopy type theory, or a version of homotopy type theory. So to start off, just ordinary one category theory is about these structures called categories, which have objects and arrows between them, just as we kind of can see here on the board. So the idea is that we kind of want to capture things like the collection of all sets with maps between them. And we know that we have composition of maps. So whenever I have a pair of two composable maps like this, I can find a third map that is the composite of those. And this I can do to sets, but then I also have kind of more interesting categories, such as the category of groups, where those arrows are not just maps, but they're maps with special properties. They're homomorphisms, the same for topological spaces. These structures could also be kind of relational structures, such as posets. Like every poset is a category. Also, posets themselves, category with monotone maps between them. So this is kind of the story from ordinary category theory. In infinity category theory, what we have is not just arrows like this, but we have these higher dimensional arrows. So we have arrows between arrows, kind of two-dimensional arrows like this, and three-dimensional arrows going between those two-dimensional arrows. And those kind of come up very naturally in particularly homotopy theory, algebraic geometry, but also in some parts of theoretical physics. So when you start thinking about kind of a good mathematical description of quantum field theories, it's very natural to consider those higher categories as well. What does it mean? It means that an infinity category is now a kind of category where I have data in all dimensions, which is already an infinite amount of data. So connected to the composition, usually there should be some laws such as associativity. Like if I have GH and I compose that with H, GF and I compose that with H, that should be the same as G composed with F of H. So of course, if I have kind of data and cells in arbitrarily high dimensions, I also need to have laws governing those higher dimensional compositions, relating them to lower dimensional compositions. So that's quite a lot of data. And what adds to the problem is that typically those compositions will also not be given as they are in ordinary category theory by some kind of algebraic, well-defined, specified operation that gives us a composite. But these composition data will be more like topological data in some sense. So they will be specified in a weaker sense, and the sense in which those laws hold are not just equalities, but they're rather something like paths you could imagine. So I'm gonna maybe draw a little squiggle here to show that this is kind of a weaker, this is kind of meant in like a weaker sense. So this is not just going to be an equality anymore, but this is kind of a datum in itself that has to cohere with other data. So you could imagine that this makes these things quite spooky in some sense, and actually even to define what an infinity category should be, you already need to know kind of a lot of one category theory. So maybe there's a better way in which we can do this. So what do I mean by better way? The point I'm making is that these infinity categories are really more to be thought of like a kind of topological structure, a kind of space-like structure, or a generalization thereof. And so everything that we're doing has to kind of respect their inherent continuous structure. So that is not the case for the language of set theory, right? So in set theory, we can kind of talk about things that are non-continuous, and there are some good reasons why we want to be able to do this. But if we want to bootstrap a theory that is tailored specifically towards reasoning about infinity categories and maybe kind of infinity homotopy versions of groups or rings or modules or something like that, we might want to have a kind of language that is a bit more tailored toward this. And this is kind of the point that I'm trying to make. So in set theory, we're building up all this kind of intricate homotopical structure from just bare sets that are just discrete in the strictest sense possible. So you can think of this as an analytic foundation where you're building up the thing, the complicated structure from some very simple structure that doesn't respect the kind of invariance property that you ultimately would like to model. And I want to transition the picture to synthetic foundations where already the language in which we're building everything natively respects this kind of notion of equivalence or homotopy or deformation. So the promise that I'm making, yes, so in synthetic foundations, the right synthetic foundations, we can actually do infinity category theory, but not just in the sense that we can replay a bunch of things that we already knew how to do in set theory, but we can really replay them in a nicer way, and we will see this kind of going forward. And what we're using is some of the things that people here I know find interesting. So this is homotopy type theory, but also results from lattice theory and modal logic, which is important. So to kind of shift our mind a little bit, I'd like to quote Yuri Manin, kind of made this point about math in the 21st century, not necessarily all of math, but big branches of mathematics that shift more and more into this direction that rather than having sets as basic foundations, we really put the spaces up to deformation as our primitive objects, and rather, instead of I'm building my continuous topological space out of discrete sets, it's a kind of reversal of this paradigm, because I'm starting with the space, and then to get a discrete set, I have to destroy some of the structure. Right? This is kind of a dual. This direction is kind of dual to how it was traditionally done, at least with respect to axiomatic set. So one of the the foundations for what we want to do is this field called homotopy type theory, which goes back to kind of the developments of type theory 100 years ago, but really has gained an important addition due to what are called Martin-Löf identity types, due to Martin-Löf in the 70s. And very recently in the past, basically 20-25 years, has gotten this homotopical reinterpretation. So there was this work by Hoffmann and Streicher in the 90s about just one groupoid model of type theory that already violated the uniqueness of identity proof principle. just in the case for kind of one categorical structures, and that was later generalized by Wygotsky and also ideas by Streicher to an infinite dimensional version, taking infinity groupoids. And Audi and Waring gave a very general interpretation of homotopy type theory with respect to kind of what are called model categories, which are kind of axiomatic categorical frameworks to doing homotopy theory. And actually about, this part of the story that isn't about categories yet, but more about kind of type theory, identity, and applications to synthetic homotopy theory. We will hear by Steve Audi himself because he's visiting in a few weeks and talking exactly here about this kind of thing. So as an example to how kind of these foundations compare, let's take the unit circle. So in kind of analytical foundations, the unit circle is defined maybe as a set of points with distance exactly 1 from the origin. So it's a point set subset of the Cartesian plane. So we kind of understand that very well, but if you try to do homotopy theory with respect to this, you can say in some sense this is not very intrinsic because this is kind of metric, and the homotopy doesn't care about metrics. So in homotopy type theory, the way to specify the circle would be via a kind of homotopical universal property by saying consists of the following data. So we have one point and we have a loop of that point, a self loop. And that freely generates the structure of the circle in an appropriate sense, which in particular, then you can show that the self loop really is non-trivial. So it's not just a null homotopy where you would just, stand at the point and do nothing, but it really, you're really going kind of around. And this is completely enough. So maybe this presentation also manifests the picture that homotopy type theory really can also be thought of as a programming language, and in fact it has various implementations in actual programming languages and libraries in which people compute homotopy groups of spheres and these kinds of things. So dependent type theory is about we structure our basic objects, every element that we talk about has to be an element of some type. Types can depend on other types. So these dependent types are really families indexed by another type. So if I have a family B like this, it's going to be indexed over some type A. And then I can do constructions with these types. So for instance, if I have two types, I can form the Cartesian product, which gives me the ordered pairs, or I can form the function types. But I also have dependent versions of this, which are very important and useful. So for the dependent pair type, I would think of B not just being a type completely separate from A, but B now would be a family of BAs that are indexed over A. And I can kind of take the sum over all these individual members and glue them together to give me like one single type. And the elements there will be, again, ordered pairs A and B, but now I'm making sure that my B comes from the type that lives exactly over A. So it comes from the fiber of B that lives over A, called BA. And similarly, I can do the same thing for functions. So I can look at functions that map an A not just into any point of this sum type or total type, but actually to the right corresponding fiber B of A. So these are kind of functions with varying, where the codomain varies in the appropriate sense, and the geometers or the topologist way of thinking about these kinds of things is that like a dependent type is really a kind of family, which can also be repackaged as a bundle or a kind of fibration, and then the sigma type would be the total type or the total space of the fibration, and the pi type would be kind of the space of sections of that bundle. And actually, if you look at actual kind of homotopical models of homotopy type theory, you get very precise correspondences of these constructions with the type formers in that sense. So the identity types now are supposed to kind of give a give a good handle on equality in an intuitionistic system. So what do we want from equality? So we want to reify the types or the kinds in which two terms of a type can be equal. So x equals to y is not just an equation anymore, but it's a type, and its inhabitants are, all the proofs or all the reasons or the witnesses or certificates that x is equal to y. So of course, canonically, x should be equal to x by reflexivity, right? So we ask this to be tracked by a specific term. And in the topological picture, you can really think of this x equal to y as a kind of as a path, continuous path. And there's one other rule. So now we know what reflexivity is, but we want to kind of know a little bit more about equality. So now what we're adding is an elimination principle, which maybe looks a bit intimidating if you look at it first. But let's decompose this. So what we're having is a family that depends on the path type of another family. And I mean, there's different ways to present this rule. Maybe this is not the most comprehensible one. But in any case, we have our family B that depends on paths in A. And we're assuming that we have a section of that family, but only at those paths that are those canonical reflexivity paths, right? So we have a kind of partial section of that family. So now the question is, can we extend this in some way to get a section on the whole family? And the answer is yes, we can. And actually, one can prove that this extension is sufficiently unique up to homotopy. So this is not immediately clear from this rule, but you can prove it using this rule. And this is something that really kicks off a lot of things. Yeah. So this is really an induction principle, just like you have induction for the natural numbers, let's say, but here the induction kind of involves induction on paths or on equalities, which are kind of like higher order objects in some sense, which is maybe a bit unusual, but yeah.
Could you write that as the induction principle?
That's the induction principle.
The rule
includes it. Yes.
Okay.
So
I have a hard time. Yeah, I don't see induction when I look at it.
Yeah. Well, it's so it's inductive in the sense that that it tells us how to map out of the path types, right? And it tells us mapping out of a path type into some other type family, because a priori that should be dependent, which is what those sections are about. It tells us that mapping out is the same as just mapping out of those parts that are only we only have to say what we do on reflexivity, right? So induction says that to map out of the naturals is just to say what do I do with zero and what do I do with successor terms. Right? And here I'm asked, so what does it mean to define a function out of the naturals? It's defining a function at zero and at the successor of some variable. And here, if you're asking, what does mapping out of a path space mean? It means defining the map just on the reflexivity terms.
Okay.
Yeah.
Thank you.
Great question. Yeah. And one kind of way to, from this one can show that you actually get an equivalence like this. It's not so important right now. There's a whole, there's a whole kind of range of interpretations that one can look at. So we can think of type theory just logically, where all the types are predicates, let's say, or propositions, I should say. So they're at most one. We can think about this kind of one level higher, where we have sets. So now we can have sort of more than one element, right? But in homotopy type theory, we kind of take the limit of this and think about our types as spaces. So this is just a summary of what I explained before. So with this path induction principle, we can do something quite interesting, because we can also define kind of an algebraic structure on these paths, because if it's supposed to be a path in the topological sense, it should be reversible. So we should have a map from path from x to y to path from y to x. And using path induction, you can do exactly this, because path induction tells you you only need to do this at reflexivity. So you get to assume that x is equal to y, and your general path in here is actually refl x. And so you map this to something that is also, again, a loop space or a loop type. So you just also map this to refl x. And that suffices to define the whole map. Similarly with transitivity or composition. And this evokes the picture that we really get the structure of a groupoid of these paths, right? And this is somewhat true, because we do get associativity and kind of unitality, but those don't hold on the nose. Those only hold, again, up to some higher paths, because every path type is itself a type, so it also has identities, right? And so on. So this evokes this kind of picture here, right, where we have like homotopy between the two paths. So a homotopy is like a two-dimensional path, and so on. This is really like this is only the first 2 dimensions of this whole infinite dimensional picture. So all in all, the slogan to take away from here is that types are infinity groupoids, weak infinite. And also, these type families behave like fibrations in the topological sense, because so what does a fibration have? It has a kind of path lifting property. If I have a path in the kind of indexing space or type, and I have a point lying over here, then I can lift this path in a continuous way, which also gives a way to kind of transport from this fiber, to this other fiber over here. And we do have these operations for general families of types by path induction again. So that's quite powerful and useful. So from all this, one can kind of see that homotopy type theory can be understood as a synthetic version of infinity groupoid theory. And as per Grothendieck's homotopy hypothesis, infinity groupoids are the same as or equivalent to homotopy types, which are spaces up to homotopy. But what about infinity categories, right? So in infinity categories, we have just like an ordinary category. I mean, the difference, a groupoid is a category in which all the morphisms are invertible. So an infinity groupoid is an infinity category in which all morphisms are invertible, but in a general infinity category, they are not all invertible. So how could we extend homotopy type theory to also be able to talk about infinity categories? We need to kind of talk about arrows, directed arrows. So one approach to do this goes back to Riehl and Schulman from 2017, even though there were kind of these ideas that have existed sometime before that also, I guess, but this was the first time when they were really worked out like this. So we're introducing a bunch of shapes corresponding to the kind of shapes we think about when we think about composition, right? So when I think about composition, I think about, well, first of all, arrows, which are, just arrows. And then I think about triangles, right? And then maybe I think about tetrahedra and things like that. So I'm introducing these shapes that really are combinatorial versions of kind of simplices. So I have delta 1, which is the arrow, delta 2, which is the 2 simplex that has a filler in here, witnessing that this is actually a commutative diagram. I also want to take some subset of this, like this lambda 1 to 1. So yeah, the notation of these names has some system to them, but that's not so important right now. we also want to have this object E, which is just like delta 1 is basically the free living arrow. My E is the free living isomorphism, right? Because this witnesses that I have some arrow here which has a left inverse and a right inverse. So I want to have all those shapes, and I also want to have higher versions of these shapes. I want to have the n simplices and actually powers of delta 1 as well. So I have n cubes, hypercubes, and so on. Okay. So with this, I'm now saying a type is called a pre-category. So in the talk, I want to be kind of not using these mouthfuls all the time. So I'm just going to call them pre-categories, but really they are pre-infinity categories or Siegel types. If this condition here holds, so this means that the canonical restriction of those shapes in the type, right? So this shape includes here. So that means if I look in a given type at all diagrams of this form, I can always restrict to just this part of the boundary here, which are the prototypical, two composable arrows. Then this should be an equivalence, a homotopy equivalence, which is something that one can define in this homotopy type theory. So yeah, basically this says, the condition says that from the point of view of such a type that we call a Siegel type or a pre-category, any any kind of pair of arrows like this already looks like a two-simplex like this, which is a full triangle, right? So that means whenever I have a pair like this of morphisms F and G, I can find some filler here, and I can also kind of fill this stuff in the middle. And then this here I can call a composite of G and F. And one can show, I mean, being an equivalence or a homotopy equivalence in that sense means that the composition data, which is the third arrow here together with the filler in the middle, they are determined uniquely up to homotopy or up to these path identity types. Okay. So that's maybe a little bit awkward because if I think about one category theory, then composition is an operation that is additional data, right? That has to be data that comes with, the definition of a category or the concrete instance of a category. But here, the point is that the types already are kind of spaces, so I can probe them by n cells. And now this is a kind of triviality condition, basically saying, the two cells actually are completely determined by just this subpart of the two cells. So now it's a prop. Being a category or a pre-category is a property now. Okay, so why are these called pre-categories and not just categories? Well, because I have these kind of two notions of equivalence or isomorphism internally to those categories that a priori don't have to line up completely. So I can either say, okay, like every type has a path type. So in particular, my pre-categories also have path types, and paths are still reversible because of path induction. So those paths behave like isomorphisms. Okay, I can do this, but I can also define a notion of isomorphism based on these arrows by just saying, okay, an arrow is an isomorphism if it has kind of a left and a right inverse. So that would be another potential candidate for this condition of isomorphism, and there's a relationship between those, but in general, this is not an equivalence, but this condition that I'm giving here will force it to become an equivalence. So if you ever heard about kind of Siegel spaces or complete Siegel spaces, this is the completeness condition, and it's actually also, you can think of this as a version of exactly Vygotsky's univalence axiom, which I didn't officially introduce, but yeah. But maybe that's right now a good point to do this. So because what we have in homotopy type theory is we have also universe types. So very roughly what this says is if A is a type, then then it is a member of a universe U. And of course, I have to, if I want to be careful, I have to kind of index everything by some cardinal and bound it in size appropriately, which I'm going to sweep under the carpet. But we have those universe types, and because there are types, they also have themselves identity types. So if A and B are types, I can look at the identity type from A and U, or from A to B with respect to U, and I can define a map by path induction to the equivalences from A to B, what are called weak equivalences, which are given by functions from A to B that have inverses, a left and a right inverse, up to homotopy. So I get such a map, but in general that won't, or in general there's no reason why this should be equivalence. But Vygotsky's univalence axiom postulates that this should be an equivalence. This is what univalence says, and rest completeness condition is exactly this condition, but just applied to an arbitrary type rather than the universe. And later on, we will see some generalization of this univalence axiom also, because here we're looking at kind of isomorphisms of the universe, paths in the universe, and characterizing them. But later on, when we actually want to kind of look at arrows in the universe, we also want to characterize them. And so
I was just wondering if maybe in this generalized univalence axiom, you're going to say that morphisms or arrows are like equivalent to functions or something like that?
Yes. Okay. Yeah. So that's what I'm saying. So I mean, that's what directed univalence will tell me exactly this. So it will tell me that kind of it's a little bit challenging. So maybe I can write it like it's a little bit challenging to find good notations to this. So I could look at the geometric arrows from A to B in the universe, right? And I basically want to say those are functions. But usually I also use the arrow for functions. But let me maybe now write fun, for like functors from, or functions. Actually, there will be functors, but functions from A to B. Yeah. So we will later, like directed univalence will tell us that for an appropriate universe, not for this universe because it's too big, but for kind of better behaved universes, we will have equivalents. Okay. And thanks. Yeah. And Miguel gave a great segue also to kind of, I mean, what should homomorphisms even be here? I guess I kind of said it implicitly, but here's the explicit definition. They should be maps. They should just be homomorphisms in a type from little a to little b should just be geometric arrows. They go from A to B. And if you look at it very carefully, those equalities here are also only homotopies. So there are different flavors of definitions, a weak one or a strict one. There's also a strict one that works, but requires some more machinery and the type theory. So for now, I'm just going to go with the weak one here. But and kind of in line with all of this, we can also now say, when is a type an infinity groupoid? It's exactly the case if it perceives every arrow to be just a point. And then from this, you can actually prove that the rest completeness condition follows automatically. So every point then automatically will be equivalent to an isomorphism. So every arrow is invertible. So synthetic version of this. Okay, are we good on those definitions?
Yeah. Can you say one more time why the definition of the infinity groupoid resembles the definition of a groupoid?
Because you can prove because actually you can prove from this property here that then the points. So I mean, this property tells you arrows are equivalent to points. but you can prove rest completeness from this. So this will tell you that arrows are equivalent to isomorphisms, right? So then this means that the arrows are the same as the isomorphisms, all up to equivalence. And so in that sense, this is true. And also you can make a kind of more externally sounding statement where you say a type is an infinity group, but if and only if it's one arrows, it's one cells like this are all invertible. So this you can also prove equivalent as characterization. So it's really, you really get infinity groupoids in all the sense. So yeah, maybe there's now something also confusing about this, because this composition only talks about two cells, but actually in an infinity category, you should also have something about higher cells. So in this version of infinity categories, I'm really talking about infinity one categories, meaning a priori I could have kind of two cells here that also have a direction like this. So I don't actually, that's actually not the notion of infinity category we're doing here. So we should imagine our two cells to always be invertible, and same for the three cells, the four cells, and so on. But the cells are still there. So there's still, I still a priori have to think about, you know, kind of n composite simplices in this setting. And if I phrase this definition externally, I can't also get away, if I really do this on the set theoretic level, if I think about what should this all be set theoretically, I would ultimately need an infinite family of conditions. But I don't need this here, because it turns out that this is before André Joyal, who had this insight a long time ago, one of the first people to think about quasi-categories very deeply. That if you phrase this all internally to the exponentials of the topos, I mean, whatever that means exactly, then it's enough to just talk about these two like composite in two dimensions, because by the kind of standard semantics of this, it will generate all the other conditions for you externally if you look at this in the set theoretic model, but you also have some resemblance of this in the type. Okay, so this definition is nice, but what does it actually give us? Actually, one can then show, and again, note that now, again, being a category or an infinity category or a pre-infinity category or an infinity groupoid, they're just properties of these types, right? It's not additional structure; they're really properties. But from this, you get the structure that you like. So you get associativity, and you get unitality. Up to homotopy. So you can produce some proofs of those, some paths. The nice thing is that any map between pre-categories will be a functor. We can also define the type of natural transformations as Hom types of these function types. And then very nicely, we automatically get the right notion of natural transformation as families of maps indexed in this way, giving rise to the naturality squares. This is kind of nice. So now we should think about relative versions of all of this, right? So before in homotopy type theory, we talked about types that are infinity groupoids. Dependent types are families of infinity groupoid indexed by other infinity groupoids. And we saw that they have like good transformational behavior because we can do this path lifting and path transport. Could we do something similar with directed arrows now for our categories? So the answer is we can. And one kind of good way to do this is with what are called covariant families. So if you ever heard the term discrete fibration, that's synonym if you want. It's actually discrete op fibrations, the way in which I'm doing this here, because I want to do covariant behavior rather than contravariant behavior, but it works the same way. So we call a family covariant if it satisfies the following lifting property. For any arrow u that we have in the base, if we're given an x like this in the fiber, then we can find a unique lift of that arrow in the total type. And by lift, I mean if we project it down, then we just get u back again. So homotopy. Okay. This has a bunch of very good consequences. So let's assume we're at least over a pre-category, so we have composition. So with this notion of covariance, it's yeah, the rest completeness condition is less important, but you can just think about, okay, infinity categories. You don't want to make it artificially complicated. So we get a bunch of nice properties, such as all of the fibers are discrete. So by discrete, I mean groupoidal. I don't mean sets, I mean groupoidal. So that means these covariant families are really families of synthetic infinity groupoids fibered over synthetic infinity categories, right? So we might have non-invertible arrows in the base type, and we might have non-invertible arrows in the total type, but within each fiber, we only have isomorphism. And another way also to think about them, so in kind of the infinity world, the analog of sets, I mean, the analog of categories in the infinity world are kind of infinity categories, okay? But the analog of sets in the infinity world are groupoids, actually, which I could call groupoid infinity or S. So my name for the universe of infinity groupoids is going to be S, because infinity groupoids are also spaces, as per the homotopy hypothesis. So that means the covariant families are really kind of functors from some category into the universe of spaces, but that's the analog of sets. So it's the vibrational version of presheaf or covariant presheaf, if you want. And they behave exactly in that way. So this transport functor that we get also behaves functorially. So you can really think about kind of constructing a functor in that way. At least if you know what the category of spaces is, which we don't know yet, but we will know later. This all behaves functorially and naturally. And as one might expect, I mean, the standard example for presheaves are the co-representable family, the co-representable presheaves. So functors of the form hom A for some fixed element A, and one can prove that they are covariant in this setting as well. So now if you think back, kind of path induction told us that if we have a family over a path space, the sections are all determined already by what they do on REFL. And one now gets the analogous thing if we replace paths by arrows, and the reflexivity by the identity arrow. So I didn't say exactly what the identity arrow is, but because, I mean, the identity arrow is supposed to be some arrow in A. So it's some element of the function type delta 1 to A. And I just define my id x at any given point in time t to just be x, right? It's the constant map at x. That's my id x. And via rest completeness, it corresponds exactly to REFL. Yeah, so we get a generalization in that sense of path induction. Maybe not quite a generalization, because we have to restrict to covariant type families. That's the important part. So that's not true for any type family, but for covariant type families. This also resembles the Yoneda lemma, or at least the fibered Yoneda lemma, because this space of sections here is like it's looking really at the natural transformations from Yoneda of B into P, and compares that to the fiber of P at B. So that's a unifying point of view also here. So this was all proven already by Real Schulman in 2017. Yeah, so Steve Audi back in the day made this conjecture that kind of what's one way to look at toposes? Well, they're kind of like set theories. So they have an internal language in which we can do intuition of set theory. So homotopy type theory then maybe should be the internal language in some sense of these higher versions of toposes, infinity toposes. So those are infinity versions of sheaf toposes. So instead of set valued sheaves, we look at space valued sheaves in the infinity sense. And now we can kind of push this one categorical level up by conjecturing, and this conjecture actually was proven fully by Mike Schulman in 2019. So Mike Schulman is going to visit us next year. He's in San Diego, so not very far. So now one might hope to kind of transfer this result and say, okay, just like homotopy type theory is the internal language of infinity toposes, simplicial homotopy type theory, which is homotopy type theory plus those simplices to be able to talk about direction and morphisms, should be the internal language of the higher topos of simplicial objects in a given higher topos somehow. So yeah, that's a bit that starts getting a bit technical, down to the nitty-gritty of kind of what the set theoretic models of these objects are. But as a slogan, you can think about simplicial HOT in that sense as a kind of directed analog of homotopy type theory. And this is true. This you can actually prove this using various results, building on Mike Schulman's results. And actually, there are some models recently constructed by Nima Rasev through filter quotients that actually are that don't look like those models, like simplicial objects. Because this, what this really says, simplicial HOT is not just about infinity categories, but it's about internal infinity categories. Right? And this is also like a very nice recurring theme of working internally or synthetically, that if I'm working kind of in traditional foundations, I can do category theory, and then I can also do internal category theory, for instance, internal category theory of topos. But I really have to then kind of come up, internalize all of my constructions by some process. But if I'm already working in an internal language, I would hope that I can just work in that internal language, and when I externalize it, it will tell me exactly something about the objects in the internal sense. And this is true about infinity categories in that setting. But actually, it's even more general, because Nima Rasev constructed some other models that don't look like internal infinity category theory. Okay, so there are also some other approaches, I should say. There are other type theoretic approaches to this kind of thing. But the one I'm talking about is the one that has been the most developed in terms of actually, replaying more and more applications of infinity category theory and constructions in that theory. There are other synthetic theories of infinity categories that are not type theoretic, strictly speaking. So one is this program of doing internal infinity topos theory by Martini and Wolf, which they wrote a lot of papers about. There's real and verities infinity cosmos theory, which is a kind of formal categorical approach. It's kind of working in a version of higher, like infinity 2 category theory of various versions of infinity categories. They also wrote a lot of papers about this and a big book. And there's kind of an approach that is in the process of being written up, but already this is kind of a big draft book, several hundred pages, by the team of Szynski, Knossen, Nguyen, and Balde, who kind of work synthetically in a system also that potentially can be made into a type theory as well. And all of these theories have some comparisons and some analogs with what we are developing as well. So what has been done so far? So Real Schulman developed basic category theory, fiber DNA dilemma, adjunctions. Cesar Bardomiano Martinez, recent graduate from Ottawa, developed limits and co-limits and exponentiable functors in that setting. Together with Ulrich, and in my dissertation, I developed the theory of fibered categories, fibered kind of fibered category theory in that sense, where the fibers are allowed to be also categories and not just groupoids. And so the more recent work is to kind of tackle exactly the issues of defining kind of those universes here, which are the infinity category of infinity groupoids, and the infinity category of infinity categories, and developing a directed, like this kind of directed analog of the univalence axiom for these universes. So yeah, that's what I'm going to talk about. Before I get to that, there's also been some formalizations. So Nikolai Kudasov developed a proof assistant specifically for this language called RZK, named after Charles Resk. Developed a lot of this Siegel space, complete Siegel space theory as well, very wealthy models for infinity categories. You can find this online. It shouldn't be too hard to install, but you can also just try it out live. And yeah, it's all completely open source and free, so we're always happy about collaborations and people getting interested. There's a whole bunch of issues of our library that can be tackled also by beginners. In fact, I should have prepared a slide for this, but just as of recently, we also opened up a call for a summer graduate school next year at the Institute, I think, for Computational and Experimental Research in Mathematics, ICERM, at Providence, Rhode Island, which basically aims at teaching infinity category theory in that style using RZK and formalization to an audience who kind of knows a little bit about one category theory, but maybe not about infinity categories. So this is your chance, if you're a grad student and this sounds great to you or just mildly interesting, apply and or talk to me. Happy to tell you more about it. Yeah. And I should also, I should also point out, I mean, what's cool about something also in formalization is that the proof of the Yoneda lemma. So this is just a version of this direct Yoneda lemma from earlier that kind of I wrote down in parallel with the path induction principle. If you looked at a proof in kind of standard literature on higher categories, kind of even to define all the relevant notions, you would have to read 100 pages, and maybe until they prove this, this would be 200 or 300 pages in. So in the real Schulman paper, is something like 80 pages, so it takes less already. But in particular, the proof in there and the proof that we formalized this proof very clearly makes transparent that actually now the proof is easier than the proof of the one categorical. So in the one categorical Yoneda lemma, what you have to do is you have to define a map from this kind of complicated set of natural transformations from Hom into the pre-sheaf, and you have to define it in some way, and then you have to so the point is to define the reverse map. So you have to define a map into this and say, okay, this actually is a well-defined map and it gives me natural transformations. So it satisfies this naturality property. But in our theory, many of these naturality properties just hold for free. So here it's just a simple type check. I mean, here defining this map, there it is. It's just this term, which is the transport term of the covariant family. And now we just have to check that it type checks, but it actually does type check, which is also kind of syntactically very easy to see. And that's it. So yeah, the proof of this infinity categorical Yoneda lemma, which is a very far-reaching generalization of the one categorical Yoneda lemma, is easier in that system than the proof for the one categorical Yoneda lemma in traditional foundations. Okay, to construct these universes, there's a little bit of background work that we have to do, because what has been done in this theory up to the point that I explained. There's been a lot of developments about kind of abstract infinity category theory, right? There's stuff about fibrations and there's stuff about adjunctions, but there are not actually, so far there haven't been any concrete infinity categories given in that system that are not already one categories, right? So maybe delta 2 is a category, or sure, it's an infinity category sort of trivially, but it's already a one. It's also already a one category anyway. So how do we get to construct this higher category, higher categories like these ones that classify groupoids and infinity categories? So for this, we kind of have to extend our model. So up to now, we looked at diagrams that were defined on the simplex category. So one way to think about this is as a category of finite non-empty ordinals with monotone maps between them. But the point is, you should think about you should think about these ordinals as simplices, and they naturally embed into those into diagrams defined on cubes, where the cubes are again combinatorial cubes, so they can be defined as powers of the ordinal 1, which is just a free arrow like this. And we get a nice embedding here as an essential subtopos, which also carries over to the higher sense. The reason is that to construct those universes internally, we'll have to exploit something that is available at the cubical level, but not on the simplicial level. And then we kind of do this, and then we completely forget about the cubical level, and then just do the actual work again in the simplicial case. But to bootstrap everything, building up these universes, we need to kind of go higher to these spaces. And we also need to kind of know when are we in the cubical layer or at the cubical level, and when are we kind of a little bit down in the simplicial level again, because because we want to know when we are sort of in actual category world. And this is a predicate that is internally expressible, and it basically says that the type is simplicial. So now those types are kind of spaces that have not just n simplices that can kind of probe by looking at their n simplices, but n cubes in that case. So type is simplicial if it perceives the cubes to be totally ordered, right? So a general cube kind of looks like this, right? And of course, that's not totally ordered, because those elements are incomparable. But if the type perceives this as totally ordered, it will think that the cube is like a simplex. So that's the right condition to state here. And okay, and what do we do now? So we kind of extended our notion of type. We can now look at these cubes, and to kind of build all these universes, we need to also extend our language by what is called modalities. So the modalities will be operators on the types, but also on the context that will allow us to change our reasoning and to introduce operations on the types that we don't know different ways of defining them. It's kind of axiomatic but also structural way to build even newer types. So I will give some. I mean, this might look very intimidating because it's a very general framework, and I will give some examples for this. But I will also spend some time talking about this framework a little bit. So I mean, maybe not too much time actually. So the idea is that I mean, what we want to internalize is we have this category of types, cubical spaces, simplicial spaces, whatever. It's some category of types, and we want to do some constructions. So for instance, for a category, we want to look at the opposite category, which consists of the same objects, but formally the arrows are all flipped in the domain and codomain. We also want to look at what's called the groupoidal core, which is the maximal sub-infinity groupoid of an infinity category, and things like this. So these are all reified by those modalities here. So the general framework talks about these different modes. The modes are the categories that you're working in. Here, we're only working in one category, so we only have one mode. And then all those morphisms are endomorphisms of that mode. So they're endofunctors. But then those endofunctors actually have a relationship with each other. So there might be some adjunction going on, and there might be some equalities and some other relations going on. So these are tracked by two cells. And often these two cells will actually be invertible. They will be kind of like equalities, but not all the time. Okay, so every application of such a modality should also correspond to forming a new type. So we have to add this as a type former. And these modalities are to be thought of as kind of right adjoints. But the left adjoints to them act on contexts where the modalities act on types. So they can't literally be adjoints in the classical sense, but they are so in a more general sense. So this is what's reified by this rule here. So the slashing on the left-hand side corresponds to kind of the left adjoint, which works on objects. And then if I remove the slash, I get to put the mu as the action of the modality of the endofunctor on the other side. And a priori, this would change the mode. So in general, in this multimodal type theory, where you can have multiple modes, you have to keep track of these mode annotations. But here we kind of forget about them because we're on one mode anyway. Right, so then we have an introduction rule. We have an elimination rule also, which requires some care. Yeah, we get various structural rules. In particular, we get a coercion. So whenever we have a cell from mu to nu, we also get an induced map on the types. And we also get composition of like modal kind of modal application. The modal type former from the formation rule coheres with the composition of the modalities. Yeah. Okay. So what operations are we actually interested in? As I said, we're interested in the opposite. We're interested in the groupoidal core. We're also occasionally interested in co-discretization, which is localizing at the boundary inclusions. And we are also, for some purpose, interested in not just the arrow category of a type, but the twisted arrow category of a type, which has as morphisms not squares as the usual arrow category, but squares where kind of one of the horizontal arrows is reversed. So those two here are maybe less of emphasis for the talk, but we need them. And we also need to kind of govern their behavior, as I said earlier, in the mode theory. So for instance, taking the core twice, right? The maximal subgroupoid should be just the same as taking the groupoid once. If I do opposite twice, I should just get back my original type or my original category. I have units and co-units from flat and sharp being adjoint. And then for the twisted arrows, I actually have some less trivial conditions than those equations here. So yeah, we don't need to know in detail what all of this is, but the point is having this theory allows us to kind of have a very efficient type system, because there's some kind of strict rewrites that we can do as per this. Yeah, and I mean, I should also mention this flat and sharp comes from this framework of axiomatic cohesion by Bill Labere that goes back a long time, where he kind of looked at kind of doing this kind of topology, having a kind of connected components and points functor on the level of toposes. This is where this comes from, and this is really a kind of higher categorical type theoretic version of this. And I should also mention, for instance, for physics, there's this mathematical physicist Urs Schreiber who thought a lot about kind of doing physics in an axiomatic framework like this. And he has he has written a lot about this kind of formalism. So now we also need to introduce some axioms for these type formers, for these modalities. I mean, first of all, we need to say that we have an appropriate interval, which is a bounded distributive lattice, which has a reversal, and it coheres with our discrete co-monadic modality flat, in the sense that being discrete with respect to flat is the same as being discrete with respect to the interval, right? So that means if a type is a groupoid in the categorical sense, it's also a groupoid in this kind of modal sense with respect to carving out the maximal subgroupoid, if and only if. Our interval is sufficiently non-degenerated, so it has exactly 2 global points. So, okay, now comes a bit of a, maybe subtle part. So the whole reason why we said a while ago we want to work with cubical types, okay, at some point in place of simplicial types, is that for cubical types, we need the special property of the interval, which is true for cubical, but not for simplicial objects, that exponentiation with I has a right adjoint, often called the amazing right adjoint or the root. If we want to, so this is true externally. Externally, we get an adjoint, no problem. But internally, we have to. We can't say this uniformly for arbitrary types, so we don't literally get a map that is the right adjoint on the universes, but only on the global points of the universes. So we have to say this not for all types of the universe, but for all type or for all just global points of the universe, which is what this flat annotation to the typing here does for the points of these function types. So this is a bit of a weaker sense in which we have an adjoint, but it's still going to be good. And actually, this is a provably necessary restriction, which was known for a while. So now we also want to internalize something that is just very convenient, and it seems kind of indispensable to have. It's this external argument that in the homotopies, I mean, these models are usually pre-sheaf or sheaf models, so the objects are kind of diagrams of some sort, and if you want to say that a map is a weak equivalence, you can test this level-wise. Right? So a map between those pre-sheaves is an equivalence if and only if it is an equivalence at every simplex or at every cube. So this is the sufficient internalization for this, also up to the flat modality. So here is another very peculiar axiom, and I think after this, I mean, there are some more, strictly speaking, there would be some more axioms that have to do with kind of modal machinery, but the ones that I've mentioned here are the most interesting. This is a very interesting one because it tells us how to classify maps into the interval. And it's also reminiscent of, if you've heard about synthetic differential geometry, the what's called the Coq-Levere axiom, that is really at the heart of synthetic differential geometry, that tells you that every function is sufficiently differentiable. So this is kind of where this comes from. There are other settings in which this is also being considered at the moment, like in synthetic differential geometry as pursued by algebraic geometry, sorry, as pursued by people in Sweden, Gothenburg, and Stockholm, I believe. Also, there are some ideas by John Sterling and collaborators to impose this to synthetic domain theory. And there's some interesting kind of more general external topos theoretic treatment of this by David J. Myers, written up recently at the blog of the Topos Institute. So what we get from this synthetic quasi-coherence Nullstellensatz is we get to compute the mapping space I to I as delta 2, for instance. So that's something that externally you can verify because you kind of know how everything looks like, but internally, I think we need this axiom because otherwise, these spaces are just underdetermined somehow. And there are generalized versions of this. So something like this was also done by Wesley Poir in his thesis on domains. So we also get to classify the n simplices in I and the n cubes in I. And this serves to show that the interval is itself actually a simplicial type. It's also cubical, but in particular, it's also simplicial. And we can prove that our delta n's, the simplices, are categories, just one categories, because their underlying types are already sets. We can also prove some other expected things about the Booleans and the naturals. They're groupoids, they're not actually categories. And being discrete in that setting already suffices to prove that one is simplicial using the model machine. So now how can we construct this category, this infinity category of infinity categories, of infinity groupoids, sorry. So we would, the naive idea would be to say, okay, we have a general universe, which is like the type of all types, the simplicial type of all simplicial types, cubical types of all cubical types. So the left type or the covariant type families are like the relative versions of infinity groupoids. If I take a covariant family and I look at its fibers, those are groupoids. So that means a groupoid is also a covariant family just over the point terminal context. So maybe I could just take the subtype of the universe with respect to the proposition of being covariant. So proposition means being covariant. It's a property of the type family. It's not some additional structure. But in general, this will give me a rather not well-behaved type. That also looks like it's very far from being a category. And maybe this shouldn't be too surprising because is_cov of A for a single type A just means that A is discrete. It doesn't see covariance or contravariance in any way. So something here, and there should be a version kind of a co and a contravariant version because we have them for the predicates as well. So somehow we have to capture having a variance over all possible contexts. And this is possible due to some constructions kicked off by Licata, Orton, Pitzer, and Spitters, and then later kind of augmented and strengthened in some way by Mitchell Riley, which is what we call amazingly covariant. And okay, I don't want to go into the depths of this construction, but basically what we're doing is we're starting with being covariant with this proposition. We kind of look what this means over the interval, and then we get a predicate from families over I, so maps from the interval to U into the universe of propositions. Because we have this amazing right adjoint on the cubical level, we get to transpose this map. And then because this amazing right adjoint behaves like a modality, restricted to the crisp elements, we get this modal map here, which gets us back to prop. And then we just take the composition of this. So we call a single type amazingly covariant if it satisfies this proposition. And this now turns out actually to be strong enough to not just say this is a groupoid. It actually tells us something like A is covariant with respect to all possible contexts. So in particular, we get some uniformity properties that we don't get for just a standard sense of covariance for which this would totally not work. So now what we can do is we can kind of go back into the simplicial world. We can look at the subuniverse of all the cubical types of types that are simplicial. So simpliciality means this thing that every square like this will be perceived as a two-simplex. That's the proposition. So this gives us the simplicial, and this type itself is simplicial. So this gives us the simplicial type of simplicial types, but it has no compositional properties. We would like it to, we would like to carve out a type that actually turns out to be a category. And it turns out that it's enough to now just take another subtype of the types that have this property of being amazingly covariant. And with this, we get the universe map like this. So I didn't explain this pointed notation, but this just says we have our subuniverse here, which is a simplicial type, together with proof that this type is an amazing covariant fibration. We then take this type S dot, which consists of a type A like this, a proof like this, and then an element of this type, together with a kind of corresponding proof. And this is supposed to be our universe of groupoids. And universe of groupoids means whenever I have a map from a category, an infinity category, into that S, a map from some category B, then this should give a corresponding covariant family or amazingly covariant family just by pullback, which is what this diagram says. So this is the standard way to think about universes in kind of type theory and category theory, and it works. It works here. So in particular, so I said a priori this notion is stronger, but for the global elements of the universe, if I externalize this for the families that I actually want this to be true externally, this just gives me also the standard notion of just covariant family or left fibration. So for the families that I'm actually interested in, I'm not being too strong. And in fact, by this classifying property, it will also have to be at least up to homotopy equivalent to kind of other standard constructions of this universe of spaces done by other more external means. Except here we've worked completely internally to the topos, at least to the topos of cubical objects. Furthermore, this property this category has good closure properties. So actually set is a topos. Category of categories is not a topos, because for instance, it's not locally Cartesian closed, whereas set is. And the same thing holds true here. So the synthetic category S also should have a bunch of good closure properties, which can show that it has them. And it's also directed univalent. So that means if I look at geometric arrows into S, then those correspond to just functors from the beginning, the point at the beginning to the point at the end. So any function from a groupoid to a groupoid is also a functor. So just having the function type here is the same as the functor type. And from directed univalence, we can prove Siegel at restness, meaning being an infinity category. So to give you an idea of the proof, we start with there's an easy direction, which is if I have a map, if I have a geometric arrow in that universe, how do I get a functor between groupoids? One can prove kind of generically from this machinery of defining this amazing covariant predicate that maps into S then have to correspond to these amazingly covariant families. So that means I get the covariant family, and then I can just take the fibers and I can take the transport. So this gives me something in this type. And if I want to go the other direction, I have to start with something. I have to kind of start with a groupoid, two groupoids and an amorphism between them, and kind of produce, like a homotopy coherent diagram into S. So what I can do is what I can do is I can look at this kind of mapping cone construction here. So I have my F going from A to B, and then I form the type that takes some B, and if I is equal to 0, it just gives me the fiber back. So kind of add 0. What what this means for a map, taking the sigma type over the fibers, it's like taking the disjoint union of the pre-images of the map. So I just get the full A here. And of course, if I go all the way to 1, this condition is not satisfied anymore. So this will just be false. So then I just get B here. So this is this is the full A. And here I just get to, as the proposition gets all the way over to false, I just say, okay, take the product of B with the terminal object. So this is kind of a mapping cone construction as evoked by that picture. Then one has to argue that these are inverse to each other, with which one can do. So what are applications of this? I mean, now we have defined a nice category. We've defined the infinity category of spaces. We also have defined its pointed variant. We would like to get some more categories, right? So we would like to get, for instance, categories of algebraic structures, because one of the major points of doing higher category theory is to do kind of higher algebra, higher geometry. So maybe for now, let's start with the lower stuff. So for instance, we have, pointed spaces I just mentioned. We have the category of pointed spaces. It's a space together with a point. But we also would like to have the homomorphisms there to be what we would like to expect, right? So this is going to be a category, which is not too hard to show, but does it have the right homomorphism types? So by kind of the rules of type theory, how the sigma types cohere with those predicates, I can show that the homomorphism type now computes to exactly maps such that the base point gets preserved up to homotopy. So I don't have to say, oh, I define a category with the following objects and the following morphisms. I just have to define the category in the right way, which I sort of can only do up to objects anyway. And then I will automatically get the right notion of morphism. This is also like very directly related to this discussion we had with Pierre Marquis for recently about the folds and kind of some people call the structure identity principle, which is basically the same version that you get, but for this like undirected unit here we also get for directed. We can also define the category of set-based monoids, and if we unravel all of this, we get exactly monoid morphisms as the corresponding maps. But we can also define higher versions of this, so infinity categorical versions of monoids and infinity groups, with some encoding that we can do by kind of doing infinity pre-sheaf category theory internally to our theory now. So I'm not going to explain exactly how these definitions go, but this is kind of the standard encoding in the literature that gives you monoids and groups. So we have these infinity categories of these objects with the right morphisms. Before I talked about kind of the fibered Unay lemma, which was this directed version of path induction. But we also now get the more traditional version of the Unay lemma, which should be about pre-sheaves, right? Because now we can do pre-sheaves internally. What we had before is we had these hom types, but from the way they were defined, they were covariant in both variables, right? But now we have the opposite. But the hom functor very famously should be contravariant in the first variable and covariant in the second. So we can do this now using our opposite modality and the universe of spaces, then associating a fibration to it. This is where we need the twisted arrow modality. And from this, we can prove the kind of functorial as opposed to the vibrational Unay lemma. We can prove density, which means that we can understand, every pre-sheaf can be written as a co-limit over representables. We can prove the descent property, which is this kind of far generalization of distributivity. And we can prove that the Unay, that the pre-sheaf categories in that sense are free co-completions, which they should be. There's also something about Kahn extensions and kind of the homotopy theory of categories, Grill's theorem A, which I'm mentioning here, but maybe I kind of want to skip this. We can also say something about colimits in spaces and use this to define another important infinity category, which is the infinity category of spectra. So a spectrum is a kind of replacement of a space that makes it more like an abelian group in some higher sense. So often in homotopy theory, you try to replace your invariants that you want to compute by those stable analogs because they're easier to handle. And spectra, the category of spectra, it's genuinely a higher category because it satisfies the property of being stable, which means that the pullbacks coincide with the pushouts, which is also a property that's only non-trivial in the homotopical world. So we can define this category because we have spaces, and we can prove that it's stable, which is this proposition here, and we can prove that it's co-complete using some of the insights from our theory about colimits. And with this, we can, I mean, another kind of way to motivate spectra is also that they parameterize cohomology theories up to homotopy. So we can also define ordinary cohomology as a functor, show that it actually is a cohomology theory in the axiomatic sense. And because of some recent work on the smashed product just in Bookhat, because the universe of spaces in our setting is kind of a model for Bookhat, we can internalize all of this and define what's called the smashed product of spectra. Okay, so getting some message here. Yeah, and we can't prove yet. So, I mean, this smashed product should also be used to actually give a symmetric monoidal structure in the infinity sense on spectra, which we can't prove yet because we haven't spelled out the definition of the symmetric monoidal infinity category, but that actually should be kind of possible rather immediately due to what I'm about to say next. So, yeah, the last big thing. The infinity category of infinity categories, right? So we have the infinity category of spaces, but what about kind of cat infinity? So in principle, one should think that it should be. So I mean, these discrete fibrations correspond to kind of groupoids fibered over a category, which corresponds to the universe of spaces or infinity groupoids. So these what are called Cartesian or co-Cartesian fibrations are now not groupoids, but actual categories fibered over a category. That's the notional fibration that corresponds to the universe of categories. So maybe we can replay this trick with amazing fibrations for the co-Cartesian fibrations. And it turns out that we actually can, even though it's kind of less direct, because being co-Cartesian is a more difficult property than being a discrete fibration. So we have to change the condition a little bit and weaken it to something called locally co-Cartesian. So for Cartesian fibrations, one kind of looks at situations like this, where we have a kind of a triangle sitting over, or we have kind of a shape like this sitting over some triangle at the base, and we kind of want to find a unique lift here. That's the general picture for co-Cartesian fibrations. And in the local case, one weakens this to this here being an isomorphism, which is this identity in the homotopical world. So we don't have to look at this skewed thing, but we can think that we have the same fiber here. So we just want to find a lift over this path here. So that's kind of the direction in which we have to change the definition here, but but this is actually enough to give us the right kind of object classifying general co-Cartesian, like actual co-Cartesian fiberations. We also can prove that it's directed univalent, and just like before, it's only from directed univalence that we get Siegelness, right? Which maybe makes sense because Siegelness was about kind of completing something like this to a full 2 simplex, and directed univalence is about knowing what what errors are in the universe to begin with. So it makes sense that I first need to classify those somehow. So we get directed univalence, then we get singleness and restness also. And we can kind of do a similar thing as the mapping cylinder here, but we have to do it for the co-Cartesian fibrations and co-Cartesian functors, which is kind of involved actually if you spell it all out, but it works. And so with this, we can have an outlook on kind of what to do next. So I already mentioned, there's synthetic infinity monads, operats, monoidal infinity categories, all this kind of stuff, which naturally actually involves these co-Cartesian fibrations. So it does make heavy use of cat infinity, which we now have, right? So all very happy cats or something. And the cat is very happy because we are now much more in the reach of cool stuff like spectra with the smash product as a symmetrical monoidal infinity category. And actually, it would be nice, sort of, as a next project to do presentable infinity categories in that sense. So then this would be itself the unit in this infinity category. Also, there was this kind of, since the inception of Hot, there was this dream of Hot eating itself. So Hot being able to talk about itself as its own foundational theory. So one could think about doing kind of higher type theories internally in this type theory, as we now have all this categorical stuff available that you usually would use if you did categorical semantics of type theory. One could also think about kind of computational versions of this, constructive versions. I didn't emphasize this in the talk, but there's a whole story there potentially to be told. And there are other connections to kind of other ongoing projects on these similar synthetic theories and DSLs. So there's work on algebraic and higher geometry, differential geometry. There's also, coming from Sweden, kind of, and Carnegie Mellon, a story about kind of condensed type theory and or kind of condensed mathematics and synthetic stone duality, synthetic stone spaces that would have some nice connections here. There's also work by Ulrich Buchholz and his students on synthetic locale theory. So all of these type theories also must interplay in some way because their models kind of do, and more formalization is to be done. So we work in this very heavily extended setting with these multimodalities, of which there is not a general implementation yet. So there's a lot of implementational challenges. And I hope I could convince you that infinity cats don't need to be as spooky anymore, at least if we kind of absorb a little bit of these homotopical and modal machineries. There's a bunch of references in the slides where you can look all this up. But for now, thanks a lot, everyone, and happy Halloween.
Okay, we have time for question, Ben.
So what's the idea behind condensed math?
The idea is to replace the category. I mean, the idea is to kind of replace topological spaces by other traditional topological space by other kinds of spaces that actually are being studied here very extensively by the group doing formal topology, because these give categories that are better behaved for doing homological algebra, for instance.
If you go through all this cubical machinery anyway, why don't embrace it and just go cubical type theory all the way?
Yeah, some people did this or started doing this, Matt Weaver and Dan Licata. The point is that cubical infinity categories are not as well understood, and it's not always clear or obvious how the cubical notions would correspond to the simplicial notion, to the simplicial notions, which are homotopically the right thing. Yeah, potentially that's an interesting route, and from a computational point of view, that's also what some people advocate for. So yeah, totally.
So when you say simplicia is the right way to do it, and cubical has to be kind of the same as simplicia. Why is that? Where does that come from? I mean, am I not free to use cubes or simplices as I like? That's my basic notions.
No, or at least we don't know in all cases. So I mean, there are also different notions of cubes, and some we understand the homotopy theory better of than others, and for some cubes we understand the ensuing notions of categories. But in general, I mean, you could argue just historically, but in general, those simplicial models are the ones that we just know very well.
Yeah, but from this answer, I get the impression it's just a convention. There's no intrinsic reason that makes simplices better than cubes.
Well, you have to know. I mean, it depends on what. So I mean, you have to know that some structures are equivalent to other structures, right? That you take as your frame of reference for saying, okay, this is. So I can take. So some of these models are known to be equivalent to the standard model, which are based on the simplicial shapes, but that is not true for all the cubical. That's not universally true for the entirety of what people call cubical sets.
I mean, the short illustration of this is if you take a square and you fold it in half along the diagonal, you will get in places you get a triangle. And in simplicials you get a triangle, but in some cubical varieties you get like this Pitzer thing, which has a hole in the middle because the synthetic inner cell it's just one thing. It's not what does it mean to identify it. It's just not known, and so you just identify kind of the more, and then you get like this back thing.
Okay, but this now sounds like that there are intrinsic problems. It's not just.
I mean, there are different ways to deal with it. Either you can say, okay, this is fine. You can say, but I want to have something like something that is equivalent to the topological spaces. And there are some varieties of cubes for which we know that this doesn't happen. There's one very forced model where we know, which we constructed by basically saying, but the kinds of folds that arise in this way are contractible now because I say so. And then there's but now we need to go into the details of what cubes are exactly, which is like also a whole zoo of things.
So the point is not just the category itself, but I need to care about two additional structures I put in the category: a homotopical one and a logical one. And yeah, those are not universally known to line up. Always. In some cases, yes, and in others, it's not.
There are some where we don't know, there are some where we know it doesn't, and there are some where we know they do. Of different variants of cubes and topological structures.
Questions? I'm curious, so the synthetic infinity categories, how do they relate to some theory like higher observational type theory? Is it more, can you interpret it in there or the other way around? Or how do these approaches compare, if one can ask that question?
Yeah, I mean, so I'm not very much up to date on higher observational type theory, but it would be natural to also think about it like a directed version of higher observational type. But I don't know. I think I asked Mike not too long ago, but I don't know. I'm not aware of this being very much worked on right now, but I don't know. But very natural question, very good question. Yeah, and it would be, I think it would be good. Yeah.
Aside from sounding very impressive, what was so desirable about constructing the infinity category?
Yeah, so it's a very important gadget to have. So if you want to do, I mean, the cool thing about category theory is that it can talk about itself by all categories or small category, or I mean, also, you know, all up to size issues, you know, all categories forming itself themselves a category of categories. So the same is true for infinity categories. And defining the category of categories in just one category is kind of easy once I know what the size issues are. But in infinity category world, it's surprisingly hard. So yeah, so it's a bit of an enigma. So what happens in general with kind of infinity categories, you don't just have one notion of what an infinity category is. So there are multiple models. So when I say models now, I don't mean models in the logical sense. I mean there are multiple categories of structures where each, you know, that are all in some sense equivalent. Where I could say, okay, so all of these, you know, have objects that I can call infinity categories, and where in each of these different categories or worlds I could make sense of some aspects of infinity category theory. But if you look at those models that very closely look like actual categories, where we have these funny shapes with compositions and stuff, it's somehow the known constructions about these categorical universes, they all kind of leave this layer of working homotopy invariantly. So either you have to kind of do something very involved in a different category and use a functor to go back and forth, or you can do something kind of more intrinsic, but then you kind of have to leave the layer of homotopy invariance for some time. And I mean, there's also a way to do this in a somewhat different type theory called two-level type theory, where you also avail yourself of second layer that is more like set theory. So basically, you have a layer of homotopy type theory and another layer that is also set theory, but that is also type theory, but it's more like set theory, extensional type theory. And then you have a relationship between those. So this you could do there. I suppose, and I think there's been some work on this done by Anenkov, Sattler, Capodotti, and Krauss. But in our type theory, we want something where everything is homotopy. And yeah, so we want to do an intrinsic construction that is also homotopy invariant of this very cool and important gadget.
So it's at the risk of a bad pun, you get a kind of categoricity, or you get like one model now in which it could work. You know,
this doesn't have to do with model theoretic categoricity. I mean, but sure. So I mean, we do get at least one desired model, which is kind of simplicial spaces. So we get at least this model, which you can say it's like a standard model of this theory if you want. Depending on what axioms you're asking for, you might get more models. So initially I mentioned this kind of idea of internal category theory in terms of internally to any infinity topos. So this definitely is a large class. So I'm not sure exactly what about the variety of all models that we get currently with this axiomatics, but they at least hold all true in the standard model, you know.
Yeah. Is cat infinity still an infinity 1 category, or is it an infinity 2 category?
No, it's an infinity 1 category because you can prove in that theory that the function, the homotypes of an infinity category are all groupoids. So, but this is actually, I mean, this is a great question. Thank you. And having said what I have said, something else is also true, because you might, so in some sense, this forces every object that is known to be a single type or a pre-infinity category or an infinity category to be actually infinity one rather than infinity two or infinity n. However, it's still true that if you look at that the single types form an exponential ideal. So whenever I have an infinity category C and I take I look at the functions from x to c, x can be actually any type, but in particular it can be a category also, then this is also a category. So somehow the theory does see some aspects of the two category or the infinity two category of infinity categories, right? But only on the level of kind of type formers and only on this externalized level, but not on the level of the structure that you would find in any given infinity category.
Was there like I mean, it wouldn't be an easy way, but like a standard way to take like a theory like this and move it up to like a two infinity category and like a.
Yeah, I don't know about a standard way, but one could think about maybe using other shapes or something like that, or maybe relativizing it in some other, looking at some kind of enriched version of this. And maybe, I mean, also what we're doing now could also enable doing some kind of enriched categories if we have symmetric monoidal. So that could be another way to work in that theory. Yeah.
Any other questions? Oh. Okay, then let's thank Chapman again.